Now that we have learned about correlation, we are now going to move on to the other concept we want to discuss in this module, causation. Remember, correlation measures the existence of a relationship between two variables. This relationship does not mean that one of the variables causes a change in the other variable, but that as one variable moves, the other also moves. Causation takes the relationship factor one step further and says that one of the variables causes a change in the other variable. An example of causation can help us to see how causation is viewed and used in analytics. Let's turn to our example of the increase in sales and the increase in commissions paid. Here again, we can see the directional trend of sales and commissions. The two variables appear to mirror each other, but to help us understand this more, we used a scatterplot visualization. As we can see here, as sales go up, we also have an increase in commissions. As our correlation coefficient showed at r equals 0.92, we have a strong positive correlation. But does this mean causation? And how can we determine this? We need to test and see if it truly was the commission driven by sales or what the company policy is on commissions paid. To determine actual causation involves going beyond the eyeball test or the correlation coefficient. We need to establish that one variable in fact caused the other variable's movement. To do this can ultimately take complex experiments and math, and therefore we will not dive into the complexities in this module. For our purposes, we want to discuss the concepts of correlation and causation and its impact in analytics. So far in this module, we have covered what correlation is and what causation is. But why do these concepts matter in the world of analytics? And do they matter at all? The answer to that last question is an emphatic yes. Let's jump into a potential real-life example and show how these concepts can be applied and the potential danger of assuming correlation equates to causation. Imagine you are an analyst that is working on a study regarding a cancer drug that was introduced into the market about 2 years ago. This drug was purported to help eliminate or lessen the severity of cancer in men who have either prostate or colon cancer. To perform your analysis, you have access to a vast amount of data at your fingertips, as all patients taking this medication have been tracked from various health perspectives. You begin to analyze the data, and you see some alarming issues. The first thing you notice in the data is the people who are taking the medication do not seem to be improving while they are taking this drug. You take the data and run some statistics and analytics against the numbers, and it doesn't appear there is any causation at work with regards to those taking the medication and a decrease in cancer. As the number of patients being prescribed this medication has increased, there has not been a statistically significant decline in cancer or symptoms within the patients. Essentially, what you are seeing is that there does not appear to be an actual causation of cancer medication use and a decline in cancer. When you compare these results against the original test results, you can see a decline did happen in the original numbers. Unfortunately, though, this appears to be a case of correlation and not causation. The second factor you notice is that along with cancer not decreasing, you are actually seeing an increase in hypertension within the patients. As you isolate the data and run some statistics and analytics against the numbers, it does appear that there is a causation at work with regards to the medication and hypertension. How could this be? How could a company release a drug that doesn't do what it says and is actually affecting the patients negatively? You decide to perform a strong analysis on the original test subjects to see why the drug would purport to lower cancer and help cancer patients. As you dig into the original data, you do notice that it does appear that the subjects taking the drug saw a decrease in cancer and improvements in overall health. So why is there a discrepancy between the original subjects and what you are reviewing now? Herein lies a problem with assuming correlation equals causation. When the original study was done, other factors were not considered as strongly as they should have been. These factors could include many different things. It turns out, as you analyze the data, you find that most of the patients who saw an improvement in their cancer situation were also impacted by these other factors. Now, this may seem to be implausible or simplified, but the reality is it isn't far from the truth in some cases, whether medicine or business. In a real-life case of a correlation but not causation occurred with women and hormone replacement therapy. Evidence was seen that women who took hormone replacement therapy also had lower coronary heart disease. The key word here is also. It did not say because of, but also. Here is a classic correlation versus causation. When this was seen, doctors started to suggest that hormone replacement therapy was protective against coronary heart disease. Eventually, when testing was performed on hormone replacement therapy and coronary heart disease, it was actually seen that hormone replacement therapy caused a statistically significant increase in coronary heart disease. This is the opposite of what was being purported. Here we can see a classic and actually detrimental case of correlation being viewed as causation. We want to explore a second example of correlation versus causation that could be seen in business. In business, managers and leaders are consistently trying to optimize the workforce. Imagine you work for a factory and your boss approaches you to run an analysis to find the most productive time of day for work for you and your coworkers. Your boss has you monitor and collect data on productivity throughout the day. Through your analysis, you find that a worker is most productive in the early afternoon hours. You turn the information over to your boss. After your boss looks at the information, your boss concludes it must be our daily stand-up meeting held at 1:15 that is driving this productivity. It must really motivate the employees. The stand-up meeting lasts about 15 minutes and fills the team in on the production of the day. Your boss decides to keep the stand-up going and have you continue your productivity analysis for the next few months. By happenstance, one week your boss is on vacation, and as you look at that week's numbers, you notice something. Even though the daily stand-up was not performed, there was no change in productivity in the afternoon. In fact, as you analyze closer, there might have been a slight uptick in productivity. Upon your boss's return, you show them the results and your boss is confused. Your boss was so sure that the stand-up meeting was causing the increase in productivity. Your boss asks you to keep monitoring productivity and decides to run 2 experiments. In the first experiment, your boss decides to not hold the stand-up for a month and to monitor the results. The second experiment is to hold the meeting twice a week for a month and see the results. After both experiments are complete, you give the data to your boss and your boss can't believe it. The first experiment, where no stand-up meetings were held, actually showed an increase of productivity of 15%. The second experiment, where 2 meetings were held each week, showed a productivity increase of 8%. Your boss is wondering why this is. There was a definite correlation between the stand-up meeting and increased productivity, but your boss made the error in assuming that correlation also meant causation. As you continue your analysis, you dig into the numbers more and find that the reason for increased productivity was not the stand-up meeting, but in fact, the lunch break itself was the cause for the increased productivity. You found that each time your production team got a break, there was a direct increase in productivity right after that break. Because of your findings, your boss has decided to put more short breaks in the schedule to help increase morale and productivity. As this continues on, you see an overall net increase in productivity and an overall lift on your team. As you can see in the examples shown here on correlation and causation, it is imperative to understand the difference between these concepts. And when we know the difference between correlation and causation, we need to ensure we speak correctly about them. In our examples, we looked at health and business, but these are not the only areas where these concepts matter. In many different environments, understanding correlation and causation is a key to success. One key takeaway is now when analyses are shared that state there is a causation, you can now be skeptical and say, is that really what is happening? With regards to the examples in our medical data and analysis, being able to tell the difference between correlation and causation can literally mean life or death. In business, being able to tell the difference between correlation and causation can bring improved business and strategy, versus the opposite effect of incorrect decision-making and potentially negative results to your business. Overall, correlation and causation are a key ingredient in analytics. You may hear over and over again correlation doesn't necessarily mean causation, and as we have shown in this module, that is the case. Some key takeaways about correlation and causation for you are: correlation is a relationship between 2 variables. As one variable increases or decreases, a second variable will increase or decrease in parallel to some degree. The strength of this parallel movement is measured by the correlation coefficient. The correlation coefficient is a numerical representation of correlation. It is represented by the letter R. The range of values that the correlation coefficient can take on is 1 to -1. A correlation coefficient where R equals 1 is a perfectly positive correlation. R equals -1 is a perfectly negative correlation. And R equals 0 signifies that no relationship exists. A positive correlation shows that as one variable increases, the second variable also increases. A negative correlation is the inverse. If a variable increases, the second variable will decrease. Spurious correlation is where correlation exists, but there is not a relationship between the variables. The correlation is spurious or false and illegitimate. Causation is a relational position between variables, but with one large difference compared with correlation. In causation, one variable causes the change in another variable. Becoming literate within correlation and causation is a key strength to helping you interpret analyses and data. We hope you have enjoyed this learning module on the important analytical concepts of correlation and causation. Please continue to review and utilize the other courses in the Click Continuous Classroom to improve your data and analytical literacy. This represents the end of the video experience associated with this learning module. Please close this browser window, return to the course,